Thank you very much. And it is a genuine pleasure to be back in these hallowed halls. I spent 2.5 very happy years here looking after the Environment, Sustainability and Energy Forum, as it was known then. And nowadays I actually sit on the Environment, Sustainability and Energy Division Council, which is I'm very pleased to do. So, I don't want to take up too much time tonight. Tonight we're here to hear from Professor Matthew Davidson. Matthew's a Professor of Sustainable Chemical Technologies at the University of Bath. Bath, sorry. I'm so northern. Great, okay, it's Bath. Matthew heads up the Centre for Sustainable Chemical Technologies, and this is a very appropriate title, obviously, for this time of year. It's also something I'm deeply excited about, because back in my academic days, I used to whip out to the forests of Yorkshire and bring home all sorts of cuttings from Sitka spruce trees to take and analyse and use all sorts of interesting chemicals from them in my research. So I'm really keen to hear on what's going on from Matthew tonight. I did ask Matthew, rather than go through a biography, I did ask Matthew for one interesting fact about himself, and he thought long and hard about this, and when I tell you, you might wonder why he thought so long about this. So, Matthew was educated at an all-girls school. He was one of 6 boys out of 600 girls at that school. So I think we'll learn tonight what that kind of education brings to this field of research. Matthew.
Thank you, Joe. It was a long time ago. Right, I would like to thank the organisers, as well as Jeff, for the introduction, for the opportunity to talk to you today. Thank you all for coming. Surprised there's so many of you here. And don't blame me for the title. I'd like to thank Michael for the title. Not just for Christmas, making the most of your Christmas tree. I think he sort of saw some of the stuff I was doing and said that would make a great Christmas lecture. I was a bit dubious, but let's assume it'd be okay. So let's have a more realistic title, Towards Sustainable Bio-Based Products. I think that's really what I'm going to be talking about today. So I'll take you through some of the issues of sustainability and talk about biorefineries and some of the things we're doing at Bath, but it'll be far more general than that. I'll try not to talk for too long, leave plenty of time for questions. I didn't think that we could compete with whiskey tasting, but it sounds like we can because we've got free wine afterwards. It doesn't even cost you 10 quid. What's more, the RSC have provided me with a prop, which we were looking at earlier, is 50% real. These ones are real and these ones are plastic. So it's a sort of hybrid Christmas tree. So you can recycle half of it and put the other half into a biorefinery, as you'll see later on. Anyway, I usually start talks by defining what I mean by sustainability, because it's a word that's bandied around a lot, and it's one that's very relevant to all of the research that we do. I direct a Centre for Sustainable Chemical Technologies. So really everything that we do is driven by the concept of sustainability. And it can get, as all these things, you can write essays and essays on sustainability. But in fact, the early definition of sustainability, which was defined by Brundtland in the UN Commission in the 1980s, is a very succinct one, and it's actually really quite subtle. And that is the ability to provide for the needs of the present without compromising the ability of future generations to meet their own needs. That was the first definition of sustainability as we sort of think about it today. And then it was even more recently than that this was defined again by the United Nations as effectively consisting of what are usually called the 3 pillars of sustainability. So in order for something to be sustainable, it has to be economically sustainable, it has to be environmentally sustainable, and it has to be socially sustainable. So that's sort of where we are with sustainability at the moment. But of course, nothing's new, and again, it's always quite useful to point this out. You could pick any one of lots of examples. This is a concept that has gone throughout humanity, and this is Teddy Roosevelt. And on his memorial, it's got a quote from him that says, "The nation behaves well if it treats its natural resources as assets, which must be turned over to the next generation, increased, not impaired in value." It's remarkably similar in sentiment to what we think of as a relatively recent thing. So in some respects he was quite enlightened. In other respects he was a bit less enlightened, but we'll brush over that. He didn't really like Native Americans and went around shooting bears, but apart from that, he was sustainable. And these three pillars of sustainability that we think of as from the 1980s, from the late 80s, no, actually the early 2000s, again, you can find throughout history. And the example I've got here is just from the Edo period of, I'm going to stand away from that, from the Edo period of Japan, where these Omi merchants who went roaming about Japan making money for themselves had this creed of what they called Sampo Yoshi, which is three-way satisfaction. And that's satisfaction for the seller, the buyer, and for society in general. And again, that's really quite analogous to what we think of as a fairly modern concept. So that's sustainability. Let's jump right in at the deep end. Where does the petrochemical industry fit into sustainability? Well, what does the petrochemical industry do? We use 85 million barrels of oil per day, which is a number that's sort of beyond comprehension, I think. There's some more other units there that are equally incomprehensible. But I think I read somewhere that it's equivalent to the flow of the Mississippi River. That's about the rate at which the Mississippi flows. And that's what we use. That's what global society uses. 90% of that we burn. Seems like a very sensible thing to do with a valuable resource, but that's what we do. We burn it. 8% of it we use essentially for plastics, and 2% gets turned into chemicals. Now, of course, the value is reversed in this. So this is low value, high volume, and as you go through to the chemicals, you can go to very high value, very low volume. So the economics of it sort of work. And these are the sorts of chemicals and plastics. I don't really need to tell you what chemicals are, do I? But, plastic bottles, personal care products, pharmaceuticals, cosmetics, you take your pick. You can name any consumer products you can think of are part of this little slice of chemicals here. But they're quite high value. And I guess the fundamental question is, are these things sustainable? Well, there's one very good reason why oil is not sustainable, and we could take the whole of fossil resources if you want, but I'll stick with oil. Oil is a finite resource, and you will all have come across the concept of peak oil, I would have thought. Peak oil is something that people know about, and people argue about it. This is the so-called hub at peak, and this is where we're consuming it quicker than we're discovering it, so the resources decrease. People argue about this, and again, it's a little bit like the definition of sustainability. You can get very caught up in the arguments as to whether, but it was 1980, and now they're saying it's 2010, and in 10 years' time it'll be 2020. I don't really like this hub at peak when you're talking about oil and sustainability. I prefer this one. It doesn't matter if it moves on this timescale. There's nothing sustainable about oil or fossil reserves. It doesn't matter whether you've got 300 years of coal left or whatever. On a sort of human timescale, this is only 1000 BC to 4000 AD, it's not a geological timescale. This sliver of a finite resource is just that, it's a sliver. So it's sensible to think of doing other things than just using oil to make the commodities that we want to make. Why else is oil not sustainable? Well, another very obvious reason, it's certainly not environmentally sustainable. I guess the first one is an economic sustainability, really, but it's certainly not environmentally sustainable. There's no question that burning oil contributes to global warming through releasing CO2 into the atmosphere. Again, I don't think this is a discussion that I need to have in this forum. You can maybe argue the toss as to what the effects of global warming are, but I think it's well established that global warming exists. There's another way of thinking about how we're using fossil reserves, like oil, and this is a sort of concept of old carbon versus new carbon, and this really ties up the economic and environmental aspects of it. So really the way we do things with the petrochemical industry at the moment is we take fossilized carbon, whether it's whatever it is, we turn it into chemical products. That might be fuel or plastics or chemicals. Sooner or later that ends up as CO2. And then the CO2 can be consumed by biomass. But the thing is, with this carbon cycle that we're sort of utilising on a huge scale today, the timescales don't work for us because fossilisation takes millions of years, and that's the problem. This carbon can be recycled, but not recycled on a sensible timescale for what we're interested in. And really what I'm going to be talking about today is utilising biomass directly for chemicals and fuel, and that's bypassing this part of the fossilised carbon through the chemical industry. And then the timescales we're talking about are acceptable for recycling carbon and having a carbon cycle that doesn't perturb the overall environment. So, this might take days to months to convert biomass into chemical products. Degradation is an interesting one. If you burn it, it might take seconds. If it's a plastic, it might take 100 years, 200 years. We'll come to that later on. But nevertheless, it will return to CO2, and then photosynthesis, you grow a crop, absorbs CO2 and creates more biomass. Depending on whether it's a microorganism that can reproduce very quickly or whether it's a tree that grows very slowly, it's days to decades. So this is a sort of this is a cycle using what people call new carbon rather than old carbon, which is what this is here. This is unsustainable, this is potentially sustainable. Another reason why fossil reserves may not be sustainable, again, this is back to an economic one really, an economic argument. Security of supply. Where is the oil? Do we have a sustainable supply even if we don't worry about the Hubbard peak? This map here is a distorted map of the world proportional to the known reserves of oil, and the colours represent the usage of oil. So, for example, green and yellow are high usage, and blue and grey is low usage. You can see immediately that there's a mismatch there, and there's a geopolitical uncertainty about whether we'll have access to the reserves we need for the petrochemical and the refining industries. So there's an issue there. One last thing about sustainability. If you still need convincing that it's a sensible thing to start looking at a biomass-based alternative to the petrochemical industry. There's a social argument about this, and the population is growing and will be 10 billion or whatever it will be by 2050, but it's also developing. People in the developing world want the lifestyle that people in the developed world have, and development needs energy. This is just a satellite map to show the energy that we're using. This is light pollution, if you like, in the places where you might expect it, Japan, Europe and North America, the developed world, just to show that development equals energy, if you like. And this is a graphical representation of the same thing. There's a human development index which takes into account all sorts of things like all sorts of things associated with well-being and development, education, health and things like that. And across the x-axis at the bottom is energy consumption. And you can see that as you develop, you use more energy. So the demand for energy in the next 50 years, 100 years, is going to go up. And why shouldn't it? Why shouldn't people develop in the way that we already like to think we have done? So there's a social aspect of this as well. We have to be able to provide the energy that's required for development. Now, this is just a bit of an aside, really. I was putting some of these slides together. Is it 3 years ago? How long's the coalition been around? Is it 3 years? About 3 years. And I was sitting in a hotel room putting these slides together, and I was worrying about energy. And the coalition had been, Dave and Nick have been around for about 3 weeks. And I was worried that, of course, the problem with energy is we're constrained by the second law of thermodynamics. We're going from low entropy to high entropy, and that's a problem. We're not consuming energy, we're just making it high entropy energy. So if we didn't have the second law of thermodynamics, there wouldn't be a problem, and we could all develop and everything would be fine. Now, the radio was on at the time, and you've probably forgotten this, but Nick and Dave, their first big thing there was nothing to do with banks or anything. They were going to repeal all sorts of laws because that naughty Labour government had brought in lots of repressive laws, and they were going to repeal them all. So, and they had a website. So rather than do the work I was supposed to be doing, what everybody always does is they sort of find something to distract them. I logged onto this website and thought, I'll type in, will you repeal the second law of thermodynamics? They wanted your ideas for freedom. And what could make you more free than not having the second law of thermodynamics? I thought I was clever, I was being a bit smug. Somebody had already done it. So somebody had already written to number 10, I think it was number 10 that this website was, somewhere in HM government. It's a government policy, you can't read this, but I can. It's a government policy to reduce carbon emissions by a large percent in short time scale. These aspirations are so unrealistic that they can only be achieved by suspending the laws of thermodynamics. And on it goes, written by somebody who understands thermodynamics. There was a response to this from some, I'm sure it wasn't Dave or Nick. Thank you for your idea. At the moment, this site focuses on which laws and regulations you think we should remove. Well, yeah, so we should remove it. To keep the discussion on track, we've closed the idea for comment. You can find it, and then it points you to the Wikipedia page about thermodynamics. And this shows you a disconnect between policy making and science, I think. That's what I think it shows you. Because it didn't understand the irony of it at all. It just pointed them to a page about thermodynamics on Wikipedia, which probably they knew more. They should be reading the page on thermodynamics. Anyway, and that was 3 years ago. And then I was sort of doing another talk a bit like this, I don't know, 2 years ago, a year ago, and there's bad news, I'm afraid. It's closed. Now, if anybody knows if any laws were repealed as a consequence of this initiative, I'd love to know. But the website just closed. I went to see if there'd been any more comments on it, but so we can no longer get our freedom. So we have to go back to reality, and we have to go back to obeying the laws of thermodynamics. But all is not lost. So there was a point to that slight digression. We don't have to use fossil reserves. Enough sunlight falls on the Earth in 1 hour to supply all of our energy needs for a year. We have this huge, great fusion reactor, convenient distance away from the Earth, that just throws energy at us, and all we need to do is collect it, and then, that's really the problem. All we need to do is collect the energy that's thrown towards us. There's plenty of energy around, of high value energy. Just another sort of random fact. Annual biomass production on land is 6 times the world's energy use. So we don't need to use much biomass, and in fact, biomass production is not very efficient. It's whatever photosynthesis is. It's 4 or 5% efficient, whatever, 2%, I don't know, it depends on what's photosynthesizing. But the annual biomass production on land, so that's not even in the water, is estimated to be 6 times the world's energy use. So there is hope, and that sort of brings us back to the discussion, I think. So what is beyond the petrochemical industry? This is a slide I showed before. What's beyond the petrochemical industry is the question as to whether we can make sustainable biofuels, bio-based plastics, and bio-based chemicals. We've been trying for a long time to make biofuels. What we're sort of understanding is that this is an integrated process. You can't just make the high volume, low value stuff. You have to make the high value, low volume stuff to pay the bills. And of course the oil industry has known this for 120 years or whatever it is. Sorry, this is my concession to Christmas. Michael, I did this for you. I had to get Christmas trees into it somewhere. We need biorefineries. Just like you have a petrochemical refinery, you can have a biorefinery. So I've got presents down the bottom. The presents are what biomass is made of, and these are the things that people use or can potentially use and already are starting to use to turn into valuable products and fuels. Lignocellulose, that's sort of straw, sort of the woody bits of plants. Fats and oils, there's a lot of fats and oils around, and I'll talk a little bit about that later on. And sugars. They're really the three basic biomass components that people are using to turn into valuable things. And they turn them into baubles. They turn them into fuel. You can turn them into plastics. You turn them into pharmaceuticals, chemicals. You could have more things on this, but I ran out of space on my Christmas tree. But that's pretty well it. You use biomass and you turn these parts of biomass into these things here, and then you've got a biorefinery, and you can make money and you can do it in a sustainable way. That's the theory. So we need biorefineries. What I'm going to do is just talk briefly about fuel and plastics and chemicals, just three examples of sort of work that's associated with things that we're doing, just to use them as examples. So I'll start off with biofuels. How can we make fuels from biomass in a sustainable way? There's lots of ways we can get energy, and one of the questions that you may well ask and is being asked is whether we really want to be making fuels from biomass. There's, of course, a reasonably long-running debate now as food versus fuel debate. But the reality of the situation is that 36% of the energy we use is for transport. Our transport works on internal combustion engines. 37% of the energy we use is oil, and it's no accident that they're the same, because we need a high-density liquid fuel to run the aeroplanes, cars, ships, and whatever else. That's the technology that we're using, and there's an inertia to that technology. If you buy a car now, it'll be on the road in 20 years' time. So regardless of all the clever things you can do with fuel cells and batteries and solar energy and electricity and whatever else you might think, in the short term, we need biofuels. There's no question about that. Or at least we need a high-density liquid fuel. And of course, what we're talking about is replacing fossil reserves with biofuels at the moment. So this is potentially what we, sort of where things are at the moment. We have two types of liquid fuel, I guess, at the moment. We have gasoline and diesel, and we need both. Replacement for gasoline is bioethanol, and in its latest incarnation, potentially biobutanol, so alcohols, which we can get from fermentation. We can also take either starch or lignocellulose, and through thermochemical means, new generation biofuels will be able to make hydrocarbons directly, so we won't need to have alcohols. And there's also a need for biodiesel, which we need new oil crops for, because we get the biodiesel from vegetable oils, essentially. And I'll just say a few words about making biodiesel from vegetable oils, because it's something that is happening at the moment. If you put diesel in your car now, you'll have probably up to about 5% of biodiesel in there anyway. This is the problem we've got. Excuse me, let me get good. We have these oil-producing crops. In the States, first-generation crops these are, so this is what we were using a few years ago. In the States, you would have used soybean, in Europe, rapeseed, and these are the yields per hectare per year. Jatropha is a crop that you can grow on drought-resistant land and has a reasonably high yield, more than these, so is potentially more sustainable. I'll just put that in for comparison. In order to, so we know the biodiesel yield per year, per hectare per year of this, and we know how much diesel we use in the UK. These numbers won't mean anything to you, but the land area we need to supply all of the UK diesel consumption at the moment is 17.5 megahectares. Just to put that into context, that is England, Wales and Northern Ireland. Not very sustainable. And you can see, and then you can see where the food versus fuel debate comes from. And fine, we can chop down rainforests in Indonesia and import palm oil, but there's other issues with that as well. Although they're not quite as clear-cut as they might be. I just want to talk about algae for a minute because it's something that you may have heard about as the panacea for all biofuels. You can get algae that produce large amounts of oil, of vegetable oil in them. Up to 40% by weight, by dry weight oil. They grow very rapidly. Algae reproduce very quickly. They don't have to grow stalks and leaves and roots and things. They're just little things that don't grow very much. So it's quite easy for them to grow oil. So this is rapeseed, and that's the yield in litres per hectare per year for that. Take over from the last slide. Here's two algal species, Chlorella vulgaris and Nannochloropsis. This is a freshwater species, this is a saltwater species. And these are estimated yields based on lab and pilot scale, and I think that's quite important because you do need to scale these up. The land area needed for Nannochloropsis, based on these estimated yields from lab and pilot scales, is 0.6 megahectares. Immediately you can see that makes it, on paper, more feasible. Just to give you an idea what 0.6 hectares is, megahectares, it's Norfolk. So, well, slightly more than Norfolk. Nobody would really care if we covered Norfolk in algal ponds if we could drive our fast cars and lorries around. But it gives you an idea of the orders of magnitude difference that you might have between algae and why people are interested in the potential. There are major issues with algae, not least the capital cost of growing algae. There's various ways you could grow it. You can grow it in open ponds, that has issues. You can grow it in closed photobioreactors, but they're way too expensive for fuel. Here's just a pipeline of what you might do. Growing it is not straightforward. You need lots of nutrients, so you need to integrate it with wastewater, for example, to get those nutrients for free. Energy in harvesting and extraction is a real problem because they're quite difficult to break open sometimes. So you're in danger of putting in as much energy as you get out. So there have to be advances made here. And there's chemical processes that need to go on as well to actually give you the biodiesel transesterification. So processing and things like transesterification have to be taken into account. And none of these things are optimized at the moment. So at the moment, we're still waiting for microalgae to fulfill its potential. But I did just want to mention it as a potential biofuel. Oh, here's just some work that we're doing in this area. We're interested in making new catalysts that will work on wet algae. We're interested in the lipid profiling and some of the biotechnology associated with developing new algal species that, for example, are easy to break open. And that's just another slide showing something that I think is important in any of these areas is none of these problems is, if you like, academic discipline specific. It needs people from all sorts of areas to come together to solve this sort of system-based problem. You can't just have biologists working on their own, you can't just have engineers working on their own, you can't just have chemists working on their own. Everybody needs to work together to optimize every aspect of a process to make it feasible and sustainable. And that means economically as well as environmentally sustainable. So we're not there with algae yet, but progress is being made. Right, so that's the fuels. We can't just make fuels on their own, we know that, we have to do other things as well. Plastics was 8% of that pie chart. Plastics is a huge, huge business. You'll see in a minute how big a problem plastics is. So if we can make bio-based plastics to compete with petrochemically produced plastics that we use today, we'd be going quite a long way down the track of making things more sustainable. This is perhaps the most economically viable bio-based plastic that's available at the moment. It's commercially available, it's called Polylactide, it's renewable, it's degradable, and it's a bioplastic. We don't need to worry too much about the chemistry. Lactic acid comes from fermentation. The chemistry to make the polylactic acid is to go through this thing called a lactide, and then you use chemical catalyst, which actually uses a heavy metal at the moment. It uses a tin catalyst to produce the polylactic acid. You can see on this, you probably can't see very clearly, it's not the clearest slide in the world, but the lactic acid from corn or from wheat or from sugar, it doesn't really matter. You can get starch, you ferment it to give you lactic acid, you react it to give you a polymer, you do something with the polymer. Then because it's degradable, you can compost it. Composting gives you CO2 again, which goes back into the agricultural products. So if you like, it's new carbon, it's not old carbon. PLA can be used for all sorts of things. It's been used for many years in the biomedical industry for high value products because it's resorbable, so sutures and things can be used and they dissolve. But as a commodity plastic, it's starting to be used for things like packaging and even in sort of engineering type applications. But there are issues with PLA. Everything sounds rosy. It's not quite as simple as that. As everything. Just a couple of slides as to why we might want a degradable plastic and a renewable plastic. This is a guy, an American photographer called Chris Jordan. If you're interested in the sort of graphic side of sustainability, I recommend you visit his website. He's got some fantastic photographs, and I've just taken a couple of animations from his website. This is one series he did, which was about plastics. Why would we want a renewable plastic? Well, 2 million plastic beverage bottles are used in the US every 5 minutes. So that's sort of 500 ml Coke bottles. We just use 2 million of them every 5 minutes in the US, never mind the rest of the world. This is what 2 million plastic beverage bottles looks like, as you'll see when it... This is every 5 minutes. We use a lot of plastic wastefully. Now, some of this is recycled, but some of it isn't recycled. Some of it goes to landfill. Some of it ends up as small plastic particles that float about the oceans for, who knows, 50 years, 100 years, 200 years. We don't know how quickly it degrades, and we actually don't know in any seriousness what environmental impact it may or may not have. But wouldn't it be nice if we could make this, instead of from oil, make it from a renewable source? I've sort of jumped the gun on this one a bit. Why do we want it degradable? 2.4 million pieces of plastic equals the number of pounds that enter the world's oceans every hour. So this is becoming an increasingly high-profile problem, is the lack of degradability and the persistence of plastic in the environment. So if things were made out of a degradable plastic, it wouldn't be there for hundreds of years, it wouldn't persist, it would disperse a lot more quickly, even if we didn't dispose of it responsibly. So, PLA is a good thing, but there's a problem with PLA. Well, there's lots of problems with PLA. One of the problems with PLA is this is to represent that its physical and mechanical properties don't at the moment compete with those of the sorts of plastics we're used to using, like PET, which is used for Coke bottles. The glass transition temperature is too low to put a boiling cup of coffee in, it will just collapse. But we're working on it. Along with other people, we've got various projects on this. We're making catalysts out of non-heavy metals. We're developing new industrial processes with these industrial partners, and we're making new materials that, for example, are more heat resistant, or they might have better barrier properties, so you can use them for fizzy drinks, All of these things are challenges at the moment. But nevertheless, PLA is commercially viable at the moment, and people are making hundreds of thousands of tons of it a year already. I don't think we need to worry too much about that. All this slide says is the projected demand for PLA in Europe is going to go up to 2022 in a sort of exponential way. But this will only happen if we have technical developments in making PLA more robust, more durable, and more suited to purpose. By the time we get to this third generation, which of course is where academics tend to work, which will be somewhere beyond here, we'll want to be making materials that are better than the petrochemical plastics that we're making today. And again, this is a point that is quite important to get across, is there's a huge drive to match the properties of the materials that we've got today made out of petrochemicals. In fact, where we really want to be looking is saying some of these natural products have potentially better properties. So we want to be advancing the properties of materials. Right. Final story, bio-based chemicals. So this is the 2% sliver. I've already told you that people tend to use fats and oils, they use sugar, they use lignocellulose to make bio-based chemicals. If you remember two things about this talk, remember that these are Christmas trees, and also remember this number, 1 billion tonnes a year. 1 billion tonnes a year is the global biogenic production of a type of molecule called a terpene. That's a lot. Seems like a lot to me. It's not as many as the barrels of oil that we've been using, but it's a lot. These are hydrocarbons. They've got no oxygen, no nitrogen, no heteroatoms in them. They're hydrocarbons, just like oil is a hydrocarbon. Interestingly, there's no major research program that exploits them as a generic biological resource for the chemistry using industries. That's just a bland statement that I've made in order to get money. To do research, not for me. Right, so that's leads us into it. Let's take a step back. What are terpenes, and why might we be interested in them? Normally, when I put up a silly slide like this, it tends to be generation dependent. When I say who's this, but I guess these guys are not generation dependent. Everybody knows who they are. Everybody knows who they are. It's Laurel and Hardy. There's a tenuous link in this. So this is Laurel and Hardy with a Christmas tree, which was apparently a short film called Big Business. That's not the tenuous link. That's another tenuous link. There's a link to terpenes, and this was a film where they were Christmas tree salesmen in Southern California, and a house got demolished and a cigar blew up, as far as I can ascertain. But that's Laurel and Hardy for you. Why am I talking about Laurel and Hardy? Does anybody know what this is? Oh, well, actually it is. It sort of is photochemical smog. But it's the Blue Ridge Mountains in Virginia. That's come on, keep up. Laurel and Hardy, Blue Ridge Mountains. It is photochemical smog, you're right, but it's sort of, if you like, natural photochemical smog, because the reason that the Blue Ridge Mountains and other mountain ranges are blue is because the Christmas trees in them are exuding isoprene, and when that reacts with ozone and all sorts of things, it creates oxidized species that scatter light through Rayleigh scattering and look blue, just for the same reason as the sky's blue. So the Blue Ridge Mountains are blue because of terpenes. Isoprene is the simplest terpene. It's a C5 molecule, and it's where a lot of the billion tons a year of biogenic production comes from, and it just disappears off into the atmosphere. It's actually quite a serious pollutant. There's many other terpenes. This one is in Christmas trees, alpha-pinene, you may be familiar with. You can buy pine fragrance, which is a spray for if you have an artificial Christmas tree, like half of this one. The other thing you should remember is that the smell of Christmas is terpenes. I mean, that is the smell of Christmas, isn't it? A Christmas tree. So if you have an artificial Christmas tree, you buy this stuff, which is alpha and beta pinene, and you spray it around, and it makes you think you've got a real Christmas tree. That's C10, so that's two of these molecules together essentially. So that's called a monoterpene. Most of these things smell. Terpenes tend to smell. Limonene is another one. Chemically related, it comes from the citrus smell. And farnesene is a third one. These are not random choices, by the way, which is the smell of green apples, as it turns out. Now, alpha-pinene is available in huge quantities. It's turpentine oil is alpha and beta-pinene, which is and crude sulfated turpentine is a byproduct of the paper industry. So it's cheap and there's lots of it around. It's a hydrocarbon, it's bio-based. Limonene, there's a fair bit around from the citrus industry. Farnesene, I'll come to in a minute. Of course, again, there's nothing new. If you polymerize isoprene, you end up with rubber. This is a rubber duck, and it's a Christmas rubber duck. I was going to wear red antlers, but I thought bar humbug. Sorry, where were we? So they're ubiquitous molecules, I think is the point I'm trying to get across, and they smell of Christmas. There's smelly oranges on this Christmas tree. You all have smelly orange. That's limonene. The question is there any advantage in using them as what I've called here sustainable chemical feedstocks? And if so, why haven't people looked at it before? And this was our reasoning, is we want to make these chemicals and polymers. At the moment, we make them out of oil or hydrocarbons. And we have what I've called here, in a very sort of bland way, a hydrocarbon toolkit. That means a lot of chemical catalysis, a lot of process, a lot of all sorts of clever things go on. But they're clever things that we've been developing over 120 years as we develop technologically. And the petrochemical industry is huge. If you'll excuse the pun, it's very refined. It knows exactly what it's doing. And the catalysts, some of the catalysts that convert the chemicals into useful chemicals and polymers are exquisite. And it would be a shame not to take advantage of them. The way most people look at bio-based chemicals at the moment is they take these things that were under the Christmas tree. They take lignocellulose, sugars, fats and oils. All of these have quite a lot of oxygen associated with them. And that's not a problem. We can make, as you've seen with the plastics and the biofuels, we can make useful, valuable chemicals and plastics and materials out of them. But what it means is we need a different technological base to do it with. We can't use the same know-how that we've got from 120 years of making oil to convert these things. So there's a time lag. We're not there yet. We can't do it. What we thought is if you could use terpenes, this is the pinene, so this is turpentine from paper manufacturing, this is limonene, I'll come to farnesene in a minute. We've got a hydrocarbon platform that we can use all the technology that we're used to using for converting oil into things straight into chemicals and polymers. So we call this a renewable hydrocarbon platform. The interesting thing about farnesene is that whereas these are byproducts of existing industries, farnesene has recently been developed through synthetic biology and biotechnology as a yeast fermentation for biodiesel. There's potentially, through industrial biotechnology, millions and millions of tons of this available in the future. At the moment, the fermentation is based on sugars, so it's based in Brazil. In the future, it might be based on lignocellulosic waste, so municipal waste, for example. But what it means is that we potentially have a huge source of natural hydrocarbons that we can feed into this platform that we want to develop. And that's the thinking behind what we want to do. What it's difficult to do with these oxygenated feedstocks is make various things that we've come to rely on over the last 100 years. Things like aromatic molecules, things like amines and amides, things like higher hydrocarbons. These are all things that are used a lot in solvents. These are used a lot in pharmaceuticals, and these are used in drilling oils, cosmetics, or plastics, all sorts of materials. And we think that we can potentially make these better from terpenes than you can from the, if you like, traditional range of bio-based feedstocks. That's just an advert, we don't need that one. I want you to remember this slide because over a glass of wine I think we'll be talking about it later on. These are some of the things we want to do with it. It's really just to get across that we want to make terpenes into bulk and fine chemicals. We can make them into polymer components, and we can make them into functional intermediates, we've called them, that we can functionalise further. All things that is difficult to do with the current range of bio-feedstocks that are available. So, I think I'm running out of time. This is the last slide. It's really just to round up what I hope I've got across. Is at the moment we use oil, and you can read any fossil reserve into that, for fuels, chemicals and plastics. Oil is not sustainable. It's running out. We need to start thinking for various reasons to do with sustainability, some of which I've talked about today, some of which I probably haven't. We need to start thinking about replacing some of the petrochemical products that we think that we use, like biofuels, bio-based plastics and bio-based chemicals. We need fuels, plastics and chemicals with bio-based alternatives. Really the only way to do that is in an integrated way, and that's to use a biorefinery type approach where you have biomass, which is a complex thing made up of all sorts of different feedstocks, and in an integrated way, if we can make high volume, low value things as well as high value, low volume things, then we might have a sustainable and feasible industry in the future. To add to these ones that people are using, I'd like to suggest that we can use terpenes as well. Bar humbug, I think, is where I want to finish. So, Merry Christmas. Thank you very much.
That was excellent. Thank you very much, Matthew. So, we do have time for questions. In fact, we've got quite a good amount of time for questions because your timing is absolutely perfect. That was planned on 45 minutes. So, the format for questions, we have got roving microphones. We do need to use them because this is a webcast, so people will need to be able to hear you, and they won't be able to do it if you're just shouting up from the back of the room. So, I'll need a show of hands about who wants to ask a question. When you are asking a question, please bring the microphone to your mouth so it records nicely for the webcast. And if you want to, it would be really nice if you could introduce who you are and maybe where you're from, but you don't have to. That's absolutely fine if you don't want to. Right, who would like to ask a question? I've got loads, but I don't want to start wading in on my stuff, so who wants to go first? Oh! Great. Thank you very much. So we've got a question in the middle row.
You mentioned very briefly the food versus fuel debate. Just wondered where your standpoint was on that. If we, in order to get hold of the biomass to create these wonderful products, we have to destroy the rainforest or other natural areas, that surely can't be defined as sustainable.
No, it's not. I think if you look at the first generation of biofuels, which I think were necessary because you have to have a transition from something that's not perfect to a development, things get better and better, then there are, of course, environmental and economic issues associated with using corn to produce ethanol, using palm oil to produce biodiesel. How much of, even if we did that perfectly, whether it would impact on food production if we enhance food production or not is a debatable issue. it's been too driven by trade agreements and economics, and that's the problem in a sort of free trade environment, is if you mandate that we want 5%, let's say, renewable fuels, and the cheapest source is palm oil from Indonesia, where you're chopping down rainforest, then that's where people will get their vegetable oil from. So that is very definitely not sustainable. But if you look at the developments towards newer generations of biofuels, then of course that gets refined as you go along. And if you can get lignocellulosic biofuels, which essentially come from agricultural waste, then the issue diminishes. So if you go back 10 or 15 years, yes, there's a problem. If you look at the technological developments that are happening now, that problem's diminishing, is what I would say.
Okay, we have a question back there with the white shirt.
So I'm Dr. Sergius. What you mentioned earlier in your lecture that also what we're looking for is not obviously a biofuel that can be obtained readily. And you mentioned quite rightly we've got the techniques which can convert hydrocarbons into the types of materials that we have. So therefore, the turbines being hydrocarbons would be ideal. But as you said earlier in your lecture, that we're looking for more superior materials. And that, of course, that entails research and using techniques and reagents that we haven't developed yet. Again, that's another issue, but obviously that would take time, of course, because we haven't got the methods at the moment.
Yeah. I mean, if you go to plastics, for example, rather than fuels, where with fuels we have internal combustion engines that have been developed to deal with the petrochemical fuels that we've got, and everything's very conservative, and automotive manufacturers would have a hissy fit if you started using anything that didn't look exactly like petrol. With plastics, for example, I think there are other opportunities where a lot of bio-derived molecules are chiral, for instance. So you can do interesting things by retaining the chirality in a plastic, in a polymer, and therefore controlling its physical properties to give you, let's say, more responsive polymers than, the plastics we use, things like PET, polyurethane, polyolefins, are pretty basic things, actually. We can be far cleverer than that, and the bio feedstocks give us more opportunities. But we haven't caught up with the petrochemical ones yet, but potentially we can overtake. Yeah.
Thank you.
Okay, there's a question right in front. There we go.
I wondered if you could comment on the political dimension in relation to this, specifically that the multinationals are so powerful that they ask shareholders who are interested in short-term results of raiding the Arctic. And at what point does the balance tip towards a sustainable one, and can anything be help to move it that way?
Yeah, a couple of observations about that. Firstly, the political and economic timescales are very different from the timescales required for technological development, and that's always a huge issue. And it's an issue with things like developing small high-tech companies. Venture capitalists aren't prepared to invest for 20 years. They want a return in 2 years, and that's not what happens. So that's a sort of economic problem. The political problems are similarly temporal, if you like, so they're time-based. Political timeframes, and you can see this with you can see it with all sorts of policies. And are far shorter than the timescales that are required for sustainability. what tends to happen is you get disruptive events and then you get huge technological advances. That's a bit of a fatalistic view of things, but you know, you start turning the lights off, then people start thinking a bit more about it.
We don't like to have that kind of lights turning off when I work at Ofgem, of course. That does not happen. There's a question here. Do put your hand up early so I can see where the questions are going to be coming. So.
Yes, Tony Fuel. I'm just wondering, is there a commercial processing plant to process wood to obtain the terpenes in the UK?
That's an interesting question because it comes back to the security of supply and the sort of geopolitical side of it. Not that I'm aware of. Of course, they're mostly in Scandinavia and Siberia and North America where they make paper. One of the things that we're looking at in this project is this is why the biotech routes to terpenes are so interesting, because they potentially then become detached from geography, because we produce quite a lot of lignocellulosic waste, and if we can ferment that using biotechnology, then we have a ready supply of terpenes. There's a global market for craft pulping waste. It's not in the UK, but it's available on global markets. But of course, if this became viable, then it will probably stay in the countries that it was produced in.
You made a very hopeful point about being able to use the same toolkit to process terpenes as have been developed for petrochemicals. How far along is that actually at a practical level?
I think really not very far along, and that's what this project's about, is the short answer. The slightly longer answer is that at least we can look at the same type of catalysis that we used to for CH bond activation and hydroformylation and things like that. So we can look at the catalysts that have been developed to convert hydrocarbons. There are issues, there are problems of separation with these big hydrocarbons that don't exist in the petrochemical industry. So it's not... I don't want people to get the impression that we can just throw terpenes into a oil refinery or petrochemical refinery and end up with the same products. That's not what I'm saying.
Yes, but you're saying can. How much has been done so far?
Quite a lot has been done. I mean, obviously the flavours and fragrance industry is very well developed and has been for hundreds of years. The issue is doing things like oxidations on a large scale, with sustainable reagents, and doing it at a cost, whether that's environmental or economic, that you can justify making platform chemicals with it. So a lot of the issues are processing ones.
There's a question right at the back. Any more questions coming up?
You were talking about using sort of the hydrocarbon toolkit, and that obviously uses sort of chemical catalysts.
Yeah.
But in terms of transesterification of like fats and oils, would it be more sustainable to use biological catalysts like enzymes?
That's a good question. In some cases, it may be. The choice between using a sort of enzymatic catalyst and a chemical catalyst is purely pragmatic. Generally, the bigger the volume and the simpler the process, the more chemical it becomes. Enzymes aren't actually used for that many things on a very big scale. But yeah, why not? Yeah, exactly.
So while we're waiting, oh no, there is another question. I'll shut up.
What do you think of the argument that using land for biofuels reduces the availability of land for food and can reduce food supply and increase the cost of food, particularly in developing countries?
I think it's a valid argument. I mean, it's never quite as clear-cut as that. The cost of food is not always directly coupled to biofuel production, but you know, you do the sums, and if you're using land to make fuel, you're not using land to grow food. Some people would argue it's actually a distribution problem, and if we distribute the food properly, then we don't have a problem. But it's a perfectly valid argument. I mean, the real problem is the absolutely huge amount of liquid fuel that we use. 90% of that 85 million barrels a day. So trying to replace oil with anything is simply not possible. It has to be a sort of whole mixture of things that replace oil.
From memory, I think that the price of food is very strongly linked with the price of fossil fuels as well, because there's so much energy that goes into the food production cycle. Fertilizer cycles, and also the moving it around the world. I am going to jump in, since no one's got their hand up. In your research and looking at the kind of the partnerships that you've been developing on polylactic acid, and also on things like the terpene work, I think it was Johnson Matthey, one of the partners. I can imagine their interest. You might not be putting up things like that, but are you also getting interest from the big petrochemical?
Yes and no.
Yeah, I'm just interested. You know, having seen the way in which some of the big companies are going in the States, for example, certainly some very big investments in bio-based and particularly enzymatic routes and so forth. You know, obviously, in my past...
Yeah, I think the big petrochemical companies tend to do strategic partnerships with the small high-tech companies and then wait and see if it works, as well as throwing lots of their own money at it.
Yeah. All right. Who's got a question? Yeah.
David Powell, Royal Tunbridge Wells. Been a member of the Royal Institute of Chemistry and the Royal Society of Chemistry now for 50 years. The motto now of the Royal Society of Chemistry is Pro Scientia et Humanitate. Although I didn't study Latin, I believe it means on behalf of civilized knowledge for humanity, which is all life on this planet. I see before me the word Christmas. Have we become a manic species? In evolutionary terms, we can only cope with speeds of 27 miles an hour. That's the fastest we can run. Possibly away from predators.
Or from us.
And to bring a religious mention into this, I see before me the word Christmas, Christ. I think he said, all we need is food and raiment. Food and clothes. Thank you, sir. We must think very, very carefully what we do technologically in the future. The only sensible use of a nuclear explosive and a rocket that I can see is if the astronomers tell us there is an asteroid heading for this planet that will cause mass destruction. Yes, use the nuclear bomb sensibly on a rocket. Thank you very much.
I'm not sure what the question was.
Well, I don't think there was a question, but
yes. Why are we proceeding in this manic technological direction?
I think there's an issue of equality and well-being here, actually. Why should a very small portion of the world be living in the way we are, and then we suddenly turn around and say, well, hang on, the other 6 billion people, or however many it is in 30 years' time shouldn't have the benefit of it when technologically there are no good reasons why we can't develop in a sustainable way to increase other people's lifespan and increase their availability of good technology. Why should they not? What's wrong with technological development? Well, they're not trivial. They're not trivial things to provide in a sustainable way for 10 billion people. You can't do that without technological development. Absolutely, yeah. Yeah.
This is feeling a lot like a conversation for a glass of wine, if I could put it that way. Or whatever beverage you would like to drink. We've got time for probably one or maybe two more questions, so has anyone got a burning question that they would regret deeply if they went away without asking? Or are you ready to go for your beverage of choice? I see. The mood of the room is with the beverage. Okay, so can we please thank Professor Davidson in the usual fashion? Thank you. And your beverages will be through those doors, back through the reception of the library and in the council room on your left, as I know well from my time here.